Our presenter today is Mike Kolsky. Mike graduated with a chemical engineering degree from Michigan Tech University and joined Novaspect shortly thereafter. Over these 15 years in the process control industry, Mike has helped customers as project engineer, project manager, site support specialist, and now a senior systems controls engineer. Mike and his team are available to help you optimize your challenging control problems as well as diagnose and troubleshoot your interactive loops. So, welcome, Mike. Thank you for being here and sharing your insights with us. I'm going to turn it over to you now.
Thank you, Robert. Welcome to our presentation, Practical Loop Tuning and its Impact on Site Performance. Today, I want to start by discussing why effective process control matters. Then, I'll introduce a simple and practical method to diagnose issues and improve performance in your plants. My goal is to show that we can choose and prioritize our performance goals and use some simple, rule-based tuning methods to achieve those goals quickly and confidently. The first question we should discuss is, why are we discussing PID control? Today we have a variety of valuable advanced control tools available to us. There are multivariable predictive controllers, fuzzy logic controllers, neural networks, and a variety of other advanced tools. Still, while each of these tools has a valuable application, the tried and true PID controller remains the workhorse of our industry. Process industry-wide, 95 to 98% of the automatic control loops are controlled with a PID algorithm. In most plants, that number is closer to 100%. Even when we get a chance to use some of the advanced tools, the advanced methods often calculate remote set points for regulatory PID controllers. Effective PID control still matters. A 1997 McKinsey report showed that 50 to 60% of a typical APC project comes from addressing variability at the base regulatory level, that is, at the control valve, instrumentation, and effective PID control. So, we're talking about PID because PID is everywhere in our world. Why does it matter that we do it well? Often, there's some product quality constraint or safety limit that we can't exceed. If control is poor, then we need to pad our operating set points to give us a safety margin from our limits. On the left portion of my drawing here, the red straight line is my set point. I need to have the set point this low so my variable oscillating process doesn't exceed my safety limit of the green line. If I can reduce variability, as I showed in the center, that gives me the opportunity to raise my set point to a more economic operating point. Actually, there are even times when the reduced variability, all on its own, even without the set point change, can save money. Temperature loops that oscillate can lead to thermal stress that degrades our equipment. Pressure oscillations can lead to mechanical flexing. Just being smoother often results in better control. Another way improved tuning can improve our business is by reducing weight. Many of your plants produce several different products or several quality grades of one product. On a grade change, my red step change line here is representing a set point change in response to a product grade change. With slower tuning, it takes a long time to get up to the new grade. All this time between the curves from here until here represents waste or reworked product. If we can control for faster set point response and get to set point sooner, the time difference from here in the bottom chart to here in the top chart represents saving, reduced waste, reduced rework, or reduced blending. Finally, Perhaps the most important job of all for control loops is to respond to the unexpected or unmeasured. There are a lot of things that could change or go wrong in our plants. Most of them we don't anticipate. Many of them we don't even measure. The automatic controls are our first and best defense against those unplanned events. In my diagram, I'm showing the center ring or the center circle as automatic controls. If the automatic controls can't reject our disturbances, the next ring is manual operator intervention. Now, the need for an operator to intervene has some impacts on how we communicate and manage alarms, so we prioritize the operator's action. It also has implications on how we staff our plants. How many operators do we need? How many adverse events can one person respond to simultaneously? If the automatic controls and the operator intervention don't solve our problems, the next ring out represents safety shutdown systems. Now, this could be a safety instrumented system, it could be a burner management system, or it could be output tracking in the base regulatory control level. At this level, our process is shut down, not making product, not making money. So if the first layer of controls, our automatic controls, are effective, the operators can spend their time managing and optimizing your business rather than babysitting problem loops, and we stay online, safe, environmentally compliant, and profitable. So the point of those previous 3 slides was to show that many of the outcomes of effective control translate into improved profitability. We stay safe, we comply with our regulatory requirements, we stay online more often, improved controls can reduce our maintenance cost and reduce our raw material costs. Best of all, it lets us make better product more often with less waste and less product giveaway. All of these improvements translate into dollars at the end of the day. But how well are we really doing? Those are our goals. That's what we're shooting for. As an industry, are we achieving those? Unfortunately, not very often. There's a very often cited survey from NTEC from 1994. NTEC surveyed dozens of paper mills in Canada and found that of all the loops they analyzed, only 20% of them actually reduced variability. 80% of automatic control loops in our plants made problems worse rather than better. The NTEC team found that 30% of the loops were problematic due to valve problems, sticky valves, sloppy valves, valves that didn't go where the control system commanded them. Another 30% of the valves actually made problems worse due to poor tuning. When there was variability or noise or disturbances in the process, these loops behaved worse in automatic control than they did in manual. Finally, the last 20% of the loops NTEC found were problematic due to a variety of configuration errors. That could have been measurement problems, improper scan rate, improper filtering, just configuration mistakes, or inappropriate control strategies. There were other studies, and there continue to be other studies, that find similar results. Another 1993 study found that 30% of the loops they found in control rooms were left in manual, presumably because the operators felt more confident in manual than they did turning their loops over to automatic control. That same study found that 20% of the loops still used factory default tuning. In other words, they'd never been intentionally tuned before. Other studies more recently are finding similar results. So, I'm motivated to do better. I can see there's an opportunity. Where can I start? I started my search with an Amazon.com search for PID tuning books. I got 648 different textbooks on PID tuning. That's a little overwhelming. I don't have time for 648 books. Of those books, I think my favorite was this book by O'Dwyer, 100 pages of alternative tuning rules discussed in 100 different rules discussed in 500 pages of text. Do we really need more rules? No, I think we can simplify. So is there a simpler method? Yes, that's what I'd like to talk about today. The Lambda tuning method that I want to discuss gives us an opportunity to use one or two very simple rules. The method allows us to easily identify valve health. If there's a mechanical problem, we recognize it early and have an opportunity to repair. The method results in predictable, stable behavior, smooth responses without overshoot. Most of all, I think the beauty of the Lambda method is it allows us to choose and prioritize our goals. We get to configure loops so they play nicely with others. That is, we can stop interactions by choosing which loops are most important to us, or we can choose to coordinate loops. Finally, I think one of the great benefits of the Lambda method is that it's easily teachable. Excuse me, I'm battling a cold today, so I'm going to just stop briefly and mute my mic so I don't cough in your ear. I apologize for the silence, but I will be right back with you. Thanks for the break. I want to start out by comparing the Lambda method to some alternative tuning methods. My example over the next several slides here is comparing some methods. I want to compare the Ziegler-Nichols method, some auto-tuner methods. What I want to use as my example, this simulation shows fuel and air control to a steam boiler's burner. Each of these steps on the screen is a change in firing rate. The boiler's asking for more fuel to make more steam. Here we're stepping down. The boiler's asking for less fuel. The red trace on the top third of the screen represents fuel control. The blue trace represents air control. And the green trace on the bottom is what's most important to me. That is my fuel to air ratio. It's really important for effective combustion control to maintain the ratio of fuel to air. Now this isn't the talk about boiler control. This same would apply to reactant feeds, to a chemical reactor, to ingredient feeds, to a food plant. There's a lot of times we have two or more ingredients coming into a process and we want them to be well coordinated. My green trace here is showing a 1-to-1 ratio is fuel and air are in the ratio I want them to be. First, let's look at some traditional techniques, including the one that's probably most familiar to many of us, the Ziegler-Nichols tuning rule. A lot of people tune just by experience or by experimentation or by feel. Some people can do well at this, a lot of us can't. Even when we do well, it's not repeatable and it's not teachable. It's hard to teach somebody that, well, a gain of 0.6 just felt right to me for that loop. Even when we do it well for one loop, that method doesn't give us a clean way to coordinate loops to behave together to achieve any of our goals. So, in the name of looking for a more objective standard, Ziegler-Nichols is the set of tuning rules that many of us fall back on. That's the set of tuning rules that many of us learned either in trade school or in engineering school. Ziegler-Nichols was developed in the 1940s. It was first applied to actually aiming gun turrets on Navy ships, and its goal was simply to get to set point as fast as possible. So if you look at my trace here, when I changed my firing rate, fuel got to set point, or at least crossed over set point within 2 seconds. Air got there in 3 seconds. But there's a lot of overshoot. The downside is my fuel-to-air ratio was very poor. There's no coordination. The overshoot, and even worse yet, the overshoot happening at different time frames. My fuel-to-air ratio was in error by as much as 40%. This means poor efficiency. It means poor emissions, and most of all, having 40% more air than I need for optimized combustion, this burner might entirely trip offline. Although fuel and air got to set point in 2 seconds, the ratio wasn't corrected until 32 seconds later. We can do better. The next thing I want to discuss a little bit is an auto-tuner solution. These are typical results from a modern control system auto-tuner. This is already worlds better. If your only other tool in your bag is Ziegler-Nichols, I'd highly recommend a much better alternative as an auto-tuner. You can see both fuel and air came to their new set point in a smooth fashion without overshoot. The problem is there's still not a convenient way to coordinate those two to play together. So we still had a 17% error right here in response to my load change. That's better than Ziegler-Nichols by a factor of 2, but we can do better. Here I'm showing you for the first time today a conservatively tuned Lambda method tuning for fuel and air. The benefit of this method is I got to intentionally choose my response rate. Even though the dynamics of the two underlying loops are different, when I move a valve in manual, fuel gets to its new steady state faster than air does. But in auto, I chose tuning so that fuel and air move together at the same rate as a coordinated pair. I came to set point 60 seconds after my change, but there was no error ever in fuel to air ratio. That is my important goal, and I was able to choose tuning constants that delivered. Finally, my fourth example on this slide is another set of Lambda tuning, but this time I chose very fast, very aggressive tuning constants. What I want to show is that even though it's tuned fast, I still got stable control without overshoot. I actually got to target faster with Lambda tuning than I could with the so-called fast Ziegler-Nichols rules. With the aggressive tuning, I didn't see an error of any more than 2% in my fuel to air ratio, and I got to set point in 24 seconds. So let's summarize some of the benefits that we just illustrated with those slides. I got to choose the response rates I want that meet my process needs. I don't just have to live with what my process or what my valves give me. Another benefit is I always have competing goals. I get to choose which ones are responsive, or excuse me, I get to choose which of my goals are most important to me. In the previous example, maintaining the proper fuel to air ratio is much more important to me than just simply saying I have fast control. I defined my goal and I achieved it. The Lambda method gives us ways to coordinate loops that have inherently different dynamics. And the final slide was an example that Lambda tuning doesn't have to mean slow tuning. We got to set point with the proper ratios more quickly with the Lambda rules than we did with the standard old school fast rules. These next couple slides are just a couple examples of real-world applications of Lambda tuning. The first one is a boiler steam drum. The top white straight line here is set point. We want the water level in the steam drum to be right in the middle of the drum. The yellow line is the actual drum level measurement. Red line is the steam flow, and the blue line in the bottom is the feed water. Now, roughly speaking, what we're trying to do here is match the feed water flow in to the steam flow out. This light blue or cyan line is the valve position that's controlling the feed water, trying to achieve that goal. This was a steam drum, as found, tuned by others with fast, maybe not necessarily Ziegler-Nichols. This was just an attempt to tune the drum fast. At this instant, right here, firing rate demand to this boiler picked up by 3%. And we saw the feed water overreact and underreact and overreact and underreact to the point where it's actually affecting the steam flow out of this and affecting the other drum, the other boilers that feed this same header. Probably the most important thing to look at here, at this point, drum level is 4.5 inches above our target. At 5 inches above our target, the safety system would shut this boiler off. And now it's not available to feed our plant anymore. The screenshot on the right is the same drum tuned and coordinated with Lambda tuning. Right here, there's a 20% increase in firing rate. A few minute pause and then 20% back down again. In the before picture, a 3% change made us unstable. In the after picture, a 20% change is barely even noticeable. Drum level stayed within 1/10 of an inch of set point. This is another real-world example. This is a chemical manufacturer. This chemical reaction has two gaseous products, and there's a very expensive polymer membrane that separates the two products. It's really important to maintain a near constant differential pressure across this membrane. As the differential pressure is changing between the two product gases, it's flexing and fatiguing and possibly even tearing this very expensive membrane. My slide here is showing the before and after tuning. As found, this pressure between the two product gases was going up and down 1.5 inches higher or 1.5 inches lower than set point. This was a simple preliminary tuning exercise that brought our control from plus or minus 1.5 inches to plus or minus 1/3 inch. The bottom trace on each of these is another downstream user that's using one of these two product gases, and what I'm showing is by fixing the problem at its source, we made control easier for the downstream user as well. Now I want to comment, we came back to this customer site and took a broader look at the entire process and made some configuration changes in addition, and we made this even better. Rather than showing you the final results, I wanted to show you these preliminary results which were achieved with tuning only. Just a handful of hours worth of work. And my final example I want to show, this one is not an actual customer demonstration. This is a simulation of something we believe we're capable of. This customer makes a solid product, and what they're doing is blending two different ingredients into a very large blend tank. What I'm showing here is there was a grade change, and it takes almost an hour to get on spec for the new product. Everything from here to here for almost an hour is off spec and waste. We believe that by Lambda tuning this loop, we can bring that set point change time from an hour down to 13 minutes, reduce 47 minutes worth of giveaway. So after all the background and all the examples, we're finally ready to talk some mechanics of how do we do this. There's two kinds of processes I want to talk about today, self-regulating and integrating. The first one, the self-regulating process, is one where you change your controller output, you change your pump speed, you change your valve position. The process variable, or the important characteristic you're measuring, trying to control, will come to a new steady state. This is typical behavior for a flow loop, a temperature loop, and most pressures. there's three things I care about when I'm trying to learn about the dynamics of this loop. The first one is, when I change my valve, how much does my process change? We call that process gain. Process gain is the change in percent valve position, it's the change in percent measurement divided by the percent change in valve output. The next thing I want to know is, how long does it take for that to change? We call that the time constant. Now, we can talk a lot about math. I'll try to simplify this just to results though. The time constant is the time it takes to get 63% of the way from your initial value to your final value. But that's kind of cumbersome to measure. What I think as a good guideline is look at how long does it take to get from your starting point until just about there. You can do that with your eyeball. Divide this total time to steady state by 4. Time to steady state divided by 4 is a very good, very useful, quick estimate of your time constant. And finally, the last thing I want to know is, how delayed is my response? We're calling that dead time. So when I moved my valve at this instant, there was some time that went by where the flow didn't change at all. That's dead time. And that's going to be very important to our modeling, very important to what level of control we can achieve. Dead time could be from oversized equipment. It could be from transmitters that are installed a long way away from the valves. Anything we can do to reduce dead time or accurately measure dead time will really improve our results. So now I know how my process behaves. Now I can use my rule. My goal with Lambda tuning is to tune so that the shape of my response in automatic mode is the same first order approach to a new steady state, just like the process behaved in manual back here. This is manual mode, a steady approach to the new steady state. This represents automatic mode. With the Lambda method, I get to choose how fast I come to steady state. So again, if I want to come to steady state in 2 minutes, take that time to steady state divided by 4. That is Lambda. So we have two time constants. Tau is the time constant in manual mode. Lambda is the closed loop time constant, or the time constant in automatic mode. This is the number I get to choose. This defines how my tuning behaves, how my process works. So the tuning rules: reset time in your PID controller is easy. It's the manual mode time constant. You're done. No calculation. Plug in one measurement. The controller gain is a simple formula that's displayed right here in the last line of this slide. What I want to point out is this is a quick measurement and some quick math. It's addition, subtraction, multiplication, division. No calculus, no differential equations, no zero pole cancellation or Bode plots or any of the other methods you learned in trade school or college. All that high power math went into coming up with this formula, but the practical result at the end of the day is a quick test and quick arithmetic to get the results that we choose. I said there were two kinds of processes. The other one we call an integrating process. Now, integrating just means to successively add up. So the best example of an integrating process is a tank level. If we have more flow going into a tank than we have going out of a tank, we just keep adding that difference between input and output. See my pointer here. As flow in increases, flow in is greater than flow out, and the process continues to increase at a constant slope. It doesn't come to a new steady state. Then I lower my valve position. Now there's less flow going in than out. My slope changes. So learning my process dynamics for an integrating process is a matter of how much does this slope change for a given output change. We also have a lambda. We have that same term we still call lambda even for an integrating process, but in this case lambda represents when I tune this loop and I put it in automatic mode and some problem happens, how long does it take me to arrest that problem? How long does it take before the problem stops getting any worse? So in this case, this flow to line represents flow out of a tank. Something else caused that to happen. I might not be able to control that or even know that it's happening. But my lambda tune loop that's controlling the flow into the tank, at 1 lambda time later, I stopped that level from getting any lower. Now I'm back on my path towards control to set point. Again, we have an arithmetic formula for integrating loops. My reset time, it's not simply a matter of plugging in one number and you're done, but it's still a simple formula. And my controller gain uses my integrating gain, change in slope divided by change in output, to come up with a simple arithmetic solution to achieve my tuning goal. So to comment on our results, I went from a world with 648 different textbooks to meet 648 different special purpose tuning needs. I went from 100 tuning rules to 2 simple models with 2 simple formulas to achieve 99% of the goals we might run into in our plants. Life is very much simplified. I can tune with a purpose quickly and confidently. Now, tuning is just a matter of judgment. I get to choose the lambda that meets my needs. And I admit, that's the catch. This is one of my favorite quotes. I see it most often attributed to Will Rogers. He said, good judgment comes from experience. Experience comes from bad judgment. We all have the right to get better. We all have the right to learn from our mistakes, from our experiments, from the things that work well. So how do we develop this good judgment to know how to choose the correct lambda time? Excuse me, I'm going to silence you one more time while I cough. Excuse me, please. So thanks. My first recommendation to develop some of this good confidence, good judgment, is initially practice on a simulator. You can make all the mistakes in the world with no consequence. When you're ready to start in your plant, I think you can still do this quickly, soon, with confidence. Just start with simple, non-interactive, non-safety critical loops. While you're doing this experimentation, while you're learning, I want you to be very intentional about your goals. I think the value of lambda tuning is to be able to choose and predict your results and then confidently see that you've achieved exactly what you predicted and planned. As you see your results meeting your goals, then you can move on to the tougher jobs. Then you can move on to the loops that interact badly with others or things that need to be well coordinated with others. So again, this is kind of just restating the be intentional about your goals comment, but test your work. As you see your work meeting your predictions, you're going to gain more skill and more confidence. Another really good practice is always keep a record of the tuning parameters as you found them. Most of the time, this simple method will get you the results you want quickly, confidently. When you're wrong, when your results don't meet your needs, at least you always have the insurance policy of being able to return it to what you found, and you know you're not leaving it worse. We can take the option of better, return to as found if it's worse. The other training or learning experience to develop this judgment, take training classes. Hopefully today's discussion is helping. And learn and apply established guidelines that others have already learned for us. Finally, the last thing I want to say is when you find yourself in over your head with a really tough task, know when to call in more experienced help. So I'm talking of learning from guidelines from others. Let me give you 4 or 5 guidelines. The first one is more of a qualitative guideline, and that is just know that good tuning is often a trade-off between speed and robustness. Tuning fast may be our goal, but the more aggressive, the more fast we are, the less margin for error we have, the more we're at risk of something going unstable or going badly when things aren't as we thought they were. So just keep in mind the trade-off between stability and speed. The next very well-established rule of thumb for Lambda tuning is don't choose a Lambda time any faster than 3 times dead time. Some other people say all the time for cascaded loops where a cascade master PID loop is calculating the set point for a slave, that the master should be tuned 5 times slower than the slave. A lot of us say that, but it's hard to quantify what that means. Well, now with the Lambda method, we have an objective, quantifiable way to tune the master 5 times slower than the slave means to choose Lambda time on the master 5 times longer than the slave. Also, to stop fighting or interaction between competing battling loops, often we can address that merely by choosing which one is more important to us and tuning that loop 5 times faster than its partner that it's fighting with. And the last rule of thumb is to coordinate 2 loops. That was the example I showed you in my fuel to air ratio up front. When I wanted the fuel and air to respond at the same time, that was as simple as choosing Lambda time to be the same for both of those loops. For self-regulating loops, an additional rule of thumb is to choose Lambda 3 times longer than your manual mode time constant. That's a very slow but very conservative, stable rule of thumb. I'm going to show you a slide in just a little bit about why that guideline is there. I want to point out we can tune faster than that. In fact, many times we can tune much, much faster than that. But keep in mind the first rule. That may mean you're giving up a little bit of stability or robustness. Finally, I just want to make one comment about level tanks. A lot of times the goal of tuning a surge tank level is to be as slow as possible. If we choose our arrest time as the maximum allowable level change divided by the maximum allowable flow disturbance, you divide a volumetric flow rate, divide a tank volume by a volumetric flow rate, I will accept a change as much as 1,000 gallons, and my maximum disturbance could be 100 gallons per minute. 1,000 gallons divided by 100 gallons a minute is 10 minutes. You can directly use that number as your surge tank arrest time, or Lambda. Finally, I just want to close out here with another series of slides that are some examples of choosing Lambda methods and getting the results we expected. My loop in the next several examples is a loop that has 2 seconds of dead time, its time constant is 10 seconds, and its gain is 1. That is, for every 1% my valve position changes, my flow also changes by 1%. I'm comparing 2 different tuning sets, both of them Lambda. The left half of each of the subsequent slides is a Lambda time of 30 seconds, or that rule of thumb I told you before, three times the manual mode time constant. Example number 2 is always more aggressive tuning. Lambda time of 6 seconds. This is very aggressive, and it's actually faster response in auto mode than we were capable of achieving in manual. First comparison is set point response. When my lambda time is 30 seconds, 4 times lambda is my time to steady state, I got to my new set point in 2 minutes, exactly as predicted. No overshoot. Change to the more aggressive tuning on the right half of the slide. Again, got to set point in 24 seconds, exactly as planned, exactly as predicted. No overshoot, it's stable. What we are seeing, though, is the valve is more active. That might have an implication on valve maintenance. More frictional wear on the valve stem might cause more maintenance later. But if that's important to us to achieve fast control, predictably, we can do it. Another goal is disturbance rejection. Those unplanned things that come up. How quickly can we reject those unplanned bad things? In this example of my flow loop, maybe there's multiple feed pumps on this header, and an operator just started one additional pump, which increased our header pressure. And that's represented by, at a same valve position, my flow just picked up by 5% here. Again, my lambda-tuned loop with a 30-second time constant recovered from that problem within 2 minutes. Similar size bump in the opposite direction, got the same results. And again, with my fast tuning, I'm still stable. I still rejected the disturbance in exactly the amount of time I predicted I would, without overshoot, without oscillation, without any back and forth wiggling. What about a slow periodic disturbance? Sometimes we don't have an unplanned disturbance or bump or upset that just happens once and it's done. Something else is happening upstream periodically. First too high, then too low, then too high, then too low. PID controllers are very, very effective at rejecting those slow responses. This is still my fast lambda tuning. This disturbance that's happening on about a 5-minute period here, when I put the control loop from manual to auto, I rejected the disturbance. So what could go wrong? Everything I've showed you so far demonstrates loops behaving as intended, as planned. Even with the aggressive tuning, everything's been smooth and predictable. What could go wrong? Well, the first thing is, what if our process gain is actually higher in the real world than it was in the specific instance where we tested it? If you're tuning very, very aggressively, you want small lambda times fast response, but now your gain is another 50% or another % higher than you thought it was, that could push you into instability. Worse than that, dead time. An increase of 50% in dead time compared to what you modeled could make an otherwise stable loop go unstable. And more often than not, what goes wrong is mechanically your valve or your VFD is in rough shape. This slide here is a typical response of what a sticky valve looks like. So, excuse me, please. Sorry about that. I think I forgot to unmute you. I'm back. Thank you, Jamie. Again, this little mini slide here is showing a sticky valve. The control system is asking for more, but it's not getting more flow because the valve is stuck, not actually moving. Eventually, we have enough pneumatic pressure to unstick the valve, but now we overshoot and then stick and overshoot and then stick and then overshoot. What I want you to see is anytime you see this in automatic mode of the output is this sawtooth triangular wave and the measurement is this square wave, that's a very, very clear warning sign of valve stickiness. How about if in an attempt to diagnose that you put the controller output in manual, yet the square wave continues? That's also a sign of a sticky valve. What that is you probably have a valve positioner. Rather than the control system sawtoothing up and down trying to get to a flow target, it's the valve positioner doing the same thing, trying to work with a sticky valve. If you see this square tooth pattern, your problem is not tuning, your problem is valve mechanics that need to be fixed at the root. You cannot fix this problem with tuning, you can only amplify it or make it worse. And the last what could go wrong slide I want to show you today is what instead of the slow periodic disturbance, what if we have a high frequency or fast disturbance? Here we show a valve in manual, and with the valve in manual there's something else happening upstream that's causing my flow to go up and down, up and down, up and down once every 12 seconds. What's important here with my aggressively tuned Lambda model is when I put it in auto, the peak-to-peak size of this noise actually got 30% worse. This is the motivation for the guideline that says choose Lambda conservatively, make it 3 times slower in auto than you had it in manual. The reason is the faster you tune, the worse this magnification gets. To the extreme of Ziegler-Nichols tuning doubles this high frequency noise. This is going to happen at when the period, the time from the peak to the next peak, is about 6 times your dead time. Faster tuning means bigger problems. And finally, one historical, just a little different perspective. Part of what I want to show with this slide was that some of this insight to be conservative with our tuning and not be too aggressive and too fast has a long, long history. James Clerk Maxwell is the physicist that popularized the electromagnetic theory. Electricity, magnetism, and light all have wave properties. That's probably where most of us have heard of him in high school physics class. He also wrote a journal article in 1868 doing a mathematical analysis of the mechanical controllers of the day, starting with James Watt's flyball governor for steam engine speed control. I just love the flowery language. We don't really speak like this anymore, but I love also the historical perspective of this understanding's been with us for decades. One paragraph in his On Governors paper was, if by altering the adjustments of the machine its governing power is continually increased, there is generally a limit at which the disturbance, instead of subsiding more rapidly, becomes an oscillating and jerking motion, increasing in violence till it reaches the limit of the action of the controller. So, in terms of today's presentation, in terms of how we speak today, let me translate. If your gain is too high, you're in trouble. When there's uncertainty, be conservative with your gain. So for the fast variability, what do? The first thing is find the problem at its source and fix it there. We won't attack that problem with tuning on this loop. A hint to where that source is the frequency of that problem. I'm going to go back 2 slides here. This oscillation that happened in manual, peak to peak every 12 seconds, when you find its true source that needs to be fixed, it will also be peak to peak every 12 seconds. Sometimes we can take advantage of process design remedies, like adding a surge tank. Often that's too little, too late from our perspective as tuning engineers. We don't have that opportunity. And finally, my point about the conservatively chosen lambda times. If we've exhausted all other possibilities and can't fix the problem somewhere else, tune lambda conservatively so we don't magnify the problem. Just want to finish today with one more brief case study. This is a very generic drawing of a cryogenic air separation plant. Very, very interactive. This distillation column on the left side is actually two distillation columns stacked on top of one another. The condenser of the high pressure column is the reboiler of the low pressure column. We've got a side stream coming off the low pressure column going off to this crude argon purifying column. Now there's a variety of different configurations for air separation units that depend on the specifics of how the argon is purified, depends on whether these oxygen and nitrogen products are gaseous or liquid. But in all of them, this is an extremely interactive, extremely difficult tuning job. I just wanted to show one slide of a before and after. This is an as-found air separation unit. This is the same unit tuned with the Lambda method. We've gone from big and scribbly to straight lines. Perhaps the most important line I want to show you here is this dark blue. This is the oxygen composition going to the argon column. At about 89%, this particular unit would have tripped offline. We got down to 89.5. After tuning, instead of having a 5% variability here, we had about a 0.5% variability here. From here on, this is an intentional operator set point change to test something else. This was an improvement of a factor of 10 over the as-found tuning, simply by using that judgment and choosing our lambda times for the various loops well. So to summarize all the things that we talked about today, I hope I've made an impression that the lambda tuning method is a simple method that allows you to achieve stable, robust control without overshoot that responds at the speed you choose. The math is simple. It can be implemented quickly and with confidence, and it gives us an objective way to choose our goals and achieve them, whether those goals are choosing something like maintaining fuel-to-air ratio is more important to me than quick set point response. It gives me the ability to decouple interacting loops or to intentionally couple loops that I want to behave together. It gives me the ability during my bump testing phase to see mechanical problems, identify them and fix them at their source. And finally, I'm saying finally, it's actually my second to last bullet there. When we are uncertain, when there are things we don't know, we can always back off and be conservative. If there's a risk of high frequency disturbances elsewhere, we can choose slow lambda times that don't magnify our problems. So we've scheduled a session 2 of this talk. Thursday, April 11th, I want to talk about the use of process design to improve control up front, but mostly I want to talk about a set of instances. When can we safely choose some very, very aggressive lambda tuning? When is that safe? When is that prudent? In that line, I'm going to talk about something we call the near integrator model. And the April 11th presentation is going to be much less talking, much more dedicated towards demonstrations and examples. Registration for part 2 is open today at www.novaspect.com. So thanks for listening in. Thanks for joining us today. If you have questions, you can either use your webinar raise hand icon, and Robert can unmute your microphone to ask your question, or you can type a question using the control panel that Robert can read to me.
Thank you, Mike, for being here and enlightening us on the different approaches to loop tuning. We do have a question.